this is 15.7. This is Stokes Theorem. So the second to last theorem of the book. So both of the last two sections of the book actually are theorems that relate integrals to one another. So the way to think about Stokes Theorem, I'll say this, then I'll sort of clarify, is think of Stokes Theorem as a 3D version of Green's theorem. The truth is actually the other way around, that Stokes' theorem is really the big theorem, and Green's theorem is a special case. But since we did Green's theorem first, it really makes more sense to think about it this way. So before we give Stokes' theorem and do some examples, there's something we need to look at first, and this is the concept of what's called an induced orientation, which sounds far more complicated than it is. And this is the way it works, is suppose you have a surface sigma, and sigma has an edge C. Suppose C is a surface with edge C. So suppose C has a chosen orientation. In other words, C has a direction that's chosen. So suppose C has an orientation, which basically again means a chosen direction. So then what happens is then sigma gets what's called an induced orientation. Say from C by the right-hand rule. So to clarify, and then I'll draw some pictures, the right-hand rule in this case basically says if the fingers of your right hand follow C, then your thumb gives an orientation to sigma. So it gives sigma an orientation. So, for example, I'm going to do this all graphically. And so imagine that your surface is, say, actually I'll draw a surface in XYZ space. And it'll just be really simple, it'll just be a simple square. But it has an edge, and the edge is C. So just to clarify, C is going to be the edge of the square. C itself doesn't contain the stuff inside. It's like a square piece of wire, like a picture frame or something like that. And let's suppose C goes this way. Now if you notice, C is the edge of a square, or rectangle, however you want to think about it. That's going to be sigma. I'll keep sigma in green. So if you picture taking your hand and curling your fingers in the direction of C, your thumb has to point up in order to do it. So this is going to be a sort of a really weird hand just to point. It'll have super long fingers. Slightly messy hand, but that's alright. So you can see that the fingers are following the direction of C as they curve around. The thumb is pointing up. So what happens is that the surface sigma, I'll redraw it over here, which we did in green. We don't necessarily need to draw another picture, but it might help. Gets an upward orientation. So sigma has what's called the induced orientation. So, second example. Suppose that we did something like, again, I'll do this in XYZ space. It'll help. If, say, it was, let's do like a quarter circle. So C again is the edge of that. And suppose it goes up here, down, and forward. And sigma in this case is in here. Sigma's green. The curve is the black edge of this. So in this case, if we try and draw a hand, and the fingers of the hand need to follow C, which means they need to wrap around and the thumb needs to point to the right. Alright, so this is my right hand right here, and what's happening is the fingers are coming over, like this. So that way the fingers are following C. The thumb is pointing left. So what happens, I'll draw this back in the original picture, is C gets an orientation that goes left. Oh, sorry, sigma as the induced orientation. Let's do one more. Now this can be visually confusing sometimes, and so luckily when we end up using this, it only has sort of a plus or minus influence, so it's not like a tragic, terrible mistake if things go terrible. So don't sort of worry overly much if it's a bit confusing at first, especially. So let me do another one. Let me do like a parabolic sheet. So we'll do something like, I'll try and draw pretty pictures because it really helps if the picture's nice. So in this case, I have to really emphasize what C is here. C is composed of really 4 pieces. Right. Imagine taking like a sheet of paper and just bending it. So C is that edge. Right. C goes, for example, in this case we could do, goes to the right, goes forward, goes down, goes back, around the bottom, and then up the side. Right. That's the C in this case. The sigma in this case would be in here. Again, think of sigma as a sheet of paper, and think of C as the edge of the sheet of the paper. And since C has an orientation, it sort of goes, this is actually really hard to see and might be really hard to draw. When your fingers follow it around, so it can help maybe a little bit, let me say this, it can help a little bit maybe to unbend C a bit, if it helps. So here's sort of a, maybe even unbend it some more. So if I unbend it just a little bit, it can help see what's going on. And then what happens is that my thumb has to point back. This is going to be a really challenging drawing. That's right. I'm going to rise to the challenge. It's a rather weird finger. So I need to go over, which means my thumb needs to point back. In this case, that's a terrible picture. Hopefully it's understandable enough. And so what happens in this case is the orientation that sigma gets goes back. Sort of back and out. So we'll do more of these as we go through Stokes Theorem to see. But the point is that to see here is that if C has a chosen direction, and if C is the edge of sigma, then sigma gets an orientation from C. And knowing this fact will help us see what Stokes Theorem says. It's necessary for doing a certain step in Stokes Theorem. Now, just for basic fact is this works in reverse too. In other words, if sigma has an orientation, you can give one back to C. But Stokes Theorem only goes this way, which means I'm only going to list this induced orientation. So now we can say what Stokes Theorem is. So I'm actually going to clear the screen, put Stokes Theorem down, and then we can do a really simple example first. So 3. Stokes Theorem. Sorry, put the apostrophe in the right place. So Stokes Theorem says the following. It says, suppose sigma is a surface with edge C. And suppose that C is oriented. Again, that means C has a chosen direction. So Stokes' theorem is our fourth way of evaluating a line integral of a vector field. And what Stokes' theorem says is, it says I can change this to a surface integral as long as I take the curl of f and in this case this is where sigma has the induced orientation. So, just a quick note about Stokes theorem problems is, and I'll say this, and then but I won't write it until we've done a problem and we have a context to what I'm about to say. But I will say this as well, is actually I'll say a couple things. So the first thing is when we do Stokes theorem problems, they're multi-step problems, and so we go through sort of 3 or 4 sort of separate steps until we get an integral that we can evaluate. And so we want to be very careful to write all those steps out and not be sloppy. The second thing is, when you do Stokes theorem really only demands that you do 2 things. It demands that you take the curl of f, and it demands that you replace C by sigma, okay? Even if it's just a description. So Stokes theorem itself is not overly complicated. It's just like the first step in sort of like a chain of steps. So let's do a really easy first example. So I'm just going to give us everything. Suppose sigma is let's say, part of the rectangle z equals 2 with x between 0 and 3 and y between 0 and 4. So it's really, really simple. We undo that. And let C be the edge. What I'm going to do is I'm going to give C an orientation. So I'll say with counterclockwise, I'm going to say CCW for counterclockwise orientation. In other words, counterclockwise direction when viewed from above. This will make sense in a second when we draw a picture. What we're going to do is we're going to find double integral over C of the vector field x squared zi plus xyj plus yzk dot dr. So here's a picture. So this is a part of z equals 2. I'll try and draw a really nice picture because it'll help. This is sigma. So sigma, again, just to be clear, is the rectangle itself. C is the edge of this rectangle. So C is it's not filled in. C is the edge, if you like, but it's not the actual sheet of paper. If you think about this as like a sheet of paper or a plank of wood or something, it's the edge of this. This is C. And C has counterclockwise orientation when viewed from above. So what this means is it goes like this, and along the back, and up front, and forward. And so we can already see here that sigma will get an orientation that will go up by the right-hand rule, but I'm not going to say that just yet. All I wanted to do is see what sigma is. So then we can say the following, by Stokes' theorem. This integral we want becomes the surface integral over sigma. So what I need to do next is I need to take the curl of this vector field. When we take the curl of the vector field, remember how this works? Might be a little rusty, so I'm going to put in some little aids. I think about having a partial x, a partial y, partial z. What we do is we take a cross product. So we take the partial with respect to y of yz, which is z, minus the partial with respect to z of xy, which is 0. The partial with respect to x of yz, which is 0, minus the partial with respect to z of x squared z, which is x squared. The partial with respect to x of xy, which is y, minus 0 in this case. So we've taken our curl. This is dot n ds. So just to be clear, in here we did the curl. And now, so I've done the curl, and all I need to do is explain what sigma is. So in this case, I could say where sigma is as given, oriented up. So if it's not clear about the up, then I need to go back to the picture, and I need to say to myself, okay, if I'm following the fingers around, let me do this in, say, purple, then my thumb needs to point up, so that my fingers can follow the direction of C. So these follow C. This gives sigma direction, or rather gives sigma an orientation. So sigma gets upward orientation. By the right-hand rule, that's the induced orientation. So, just for reference, Stokes theorem is done. Right? So Stokes, done. We haven't done the problem, of course, but just in terms of keeping things tidy, Stokes is finished. So next what we do is we then say, okay, this is now a new surface integral of a vector field. So now we parameterize the surface. Right now, we're back in 15.6. We're just literally one section back. We're just doing exactly what we did before. So I'm going to parameterize this. I'll use x and y because they have nice inequalities, because the z is just 2. Oh, just so we're clear, back on this picture, the x direction goes to 3. The y direction goes to 4. And this is a height of 2. This wasn't really needed for anything we did, but it helps clarify. So my parameterization will be xi, yj, 2k. So, and this is with x between 0 and 3, y between 0 and 4. Those two inequalities, they form the region R back in 15.6. We then take the partials. Take the cross product. The cross product is really nice in this case. We get 0i plus 0j plus 1k. And we notice that this points up, which matches sigma's orientation. Remember, in 15.6 we have to look at this. So this bit specifically here tells us this is up. This matches sigma's orientation, which means we're going to use plus in the next step. So the next step, remember how this works. We get a plus. My integral over sigma changes to an integral over r. And then what I'm doing is I'm taking, just to be clear, I'm taking this vector field and I'm replacing x and y and z by the I, j, k components from r. So I have a zi, so that becomes 2i. I have a plus x squared. That becomes plus x squared because x gets replaced by x. I have a plus y, that's plus y. This gets dotted with this cross product that we just did. dA. Then we iterate the integral. I'm going to keep writing the plus, it's not necessary, but just a reminder that it's there. That x and the y each go from 0 to 3 and 0 to 4 respectively, so everybody's a constant. It doesn't matter which order we choose. And then when I dot these, it's actually really nice. When I dot these, I just get y, and then dy, dx. And now from here on out, this is just an evaluation. And that's the entire problem. So I'm going to do a couple more, but before I do, I just want to point something out about how this is a multi-step problem. Right, so let me go back and point some things out. So we started with a line integral right there. The first step is Stokes Theorem. Stokes Theorem takes us to a surface integral. Then we parameterize. That takes us to, if you like, you could call it like a region integral. That isn't really a name, but it's an integral over R. And then we iterate it. So really there are 4 steps. I'm not going to surround evaluation because that's grunt work. So the 5th step is really evaluation. But try not to skip any of these steps as we go. Like, it's really tempting to hop over them and jump straight from the integral over sigma to the iterated integral. It's so easy to make mistakes if you sort of jump steps and forget to replace variables and so on and so forth. It's so easy to screw things up, especially as the problems get more complicated. So by breaking it into steps, it gives you a time to say, like, okay, Stokes is done. Now let's move on to something else. Okay, the next step is done. Let's move on to something else, etc. So let me clear the screen, do another problem. I'm going to do 2 more in total. So for the next example, I'm going to describe it a little more confusingly. We're going to say find. So first of all, I'm going to give the integral in a different way. Because remember, line integrals of vector fields can be written 2 different ways. And I'm totally mixing them up. Let me be totally not sloppy. So this is the integral over c of z dx plus xz dy plus 2y dz. So c is going to be the intersection of x squared plus y squared equals 4. That's a cylinder with z equals 9 minus x. That's a plane. So, and let's say with counterclockwise orientation, just like before, when viewed from above. So first I'll draw this thing again because it helps. Absolutely in this case. Because notice, compared to the previous problem, I haven't said anything about what sigma is. I've just given you what C is. So C is the intersection. I'm going to draw these cylinders, these objects rather, really lightly, because then we can emphasize the intersection. There is the cylinder. Goes forever up and down, but that's all I need. Now Z equals 9 minus X. That's a plane, which as X comes forward, Z goes down. So this plane comes forward at an angle. It cuts through the cylinder. When it cuts through the cylinder, it makes like an ellipse. So that's the C, and it's counterclockwise when viewed from above. So that's the C in blue. And so, just to label everything here, this is the plane, Z equals 9 minus X. Sorry, that's especially bright. And the cylinder is X squared plus Y squared equals 4. That's that cylinder. And C is the intersection. So you can easily picture this as like a vertical tube, and you slice a piece of paper through it, and the piece of paper, that intersection, falls with an ellipse. The ellipse is not filled in, it's just the edge. And what we want is the integral over that c. And now what I'm going to do is I'm going to rewrite that integral up at the top in maybe a more familiar or a different way, but I want to do it this way so I recognize that it's a vector field. Alright, so keep in mind that this guy up here and this guy down here, these are exactly the same things, just different notation. So, by Stokes Theorem, this gets changed into the integral over sigma, and again, I need to take the curl here. So I take the curl of this, and again, if it helps, by all means, put a little d dx, d dy, d dz up here, and take a cross product, however you remember. So I take partial y of 2y, and I get 2 minus x I, instead of big bracket. Partial x of 2y is 0 minus 1 j, and partial x of xz is z minus 0 k. That's dot n ds. And now this is where sigma is, now we need to think, well, what's the sigma here, right? So sigma needs to be chosen so that the edge of sigma is c. So the c can be thought of as the edge of the ellipse that's filled in. And we can think of that as the piece of the plane which is inside the cylinder. Right? So sigma is the part of the plane inside the cylinder. Let me draw another picture just to clarify that, right? So let me draw it up next to this picture, because that'll help us see them side by side. So the C that we have is this guy, and I'm going to use light green again. This light green, this is the piece of the plane which is inside that pink cylinder. Now, and so again, so here, like, I'll put the picture here. I'm sort of cramming things together a little bit because I want to fit, as much as possible, I want to fit the entire problem on one screen so we can see it all together. So, in this case, sigma is the part of the plane that's inside the cylinder, and we choose that so that C is its edge. Now, again, by the right-hand rule, if my fingers follow C, sigma gets an upwards orientation. So just to be really, really clear, sigma is this little disk. It's an elliptical disk. So in this case, by the right-hand rule, by RHR right-hand rule, sigma gets the induced upwards orientation. And again, if it helps, then by all means, we could draw more pictures. We could be like, hey, look, here's a sort of a separate picture. Here is C going around. Here is sigma. I'm going to use dark green because that light green's hard to see. And that's the induced orientation is up, according to the right-hand rule. So, Stokes theorem is done. Let me just rewrite it up here. We've got to here. I'm just going to tidy up the integral because this is 2 minus xi plus 1j plus zk dot n ds. So then, just like before, what do we do next? We parameterize sigma. So now this is a bit confusing, right? So we need to parameterize sigma. So sigma is kind of like a disk in a way that's on an angle. It's actually an ellipse shape, but if you were to look straight down from the vertical, from the z-axis, you would see a disk because you see inside the cylinder. And that's inside x squared plus y squared equals 4. So what we can do is I can use r and theta. For x, I can use r cosine theta. For y, I can use r sine theta. And then for z is 9 minus x. So that's 9 minus r cosine theta. This is with r between 0 and 2, theta between 0 and 2 pi. So this might be a bit confusing. So take a second to see this. I'm going to call that is our r. So if this is a bit confusing, the way to look at this is to notice that the I and the j components, let me label these two, those form a disk in the xy sense. And then this z component, this forces z to be 9 minus x, and x is r cosine theta, which puts it on the plane. So that's the way we get that little circle, that little ellipse shape. So then we take our derivatives. So this is a bit messy, right? As we go, we're going to see it looks messy and then it cleans up. So r sub r, I have to be really careful here. So this is the derivative with respect to r. So this is going to be cosine theta, that's the constant, plus sine theta j, minus cosine theta k. Because derivative of 9 minus r cosine with respect to r is just the cosine. R sub theta. So this is negative r sine theta plus r cosine theta. In this case, plus, because the derivative of cosine is negative sine, r sine theta k. Now, when we cross these, this looks absolutely horrendous, right? But it turns out, and this is not infrequent, that this is nicer than you might expect, right? So when I cross these, for the I component, I get sine times r sine, which is r sine squared, minus a minus, let me write this down, this is r sine squared theta, minus a minus r cosine squared theta, I. So that's just r. For the j, we have r sine cosine. Now there's a, oops, this should be a minus right here. And then, so we have r sine cosine minus a minus times a minus. So there's 3 minuses there. R sine cosine. That's 0. That's really nice. And for this last one, we have r cosine squared minus a minus r sine squared. Oops, that's the k. That previous one, that was a j. Got all carried away there. So this is really, really nice. This turns out simply to be ri plus no j's plus rk. Now, what we need to do is we need to look at this, and we need to notice that these things, because the x and the z are both positive, because r is positive, these have an upwards forwards direction. These match sigma. They match sigma's orientation. So we're going to use plus. Remember in 15.6 we need to check this. And so what happens is we get plus, get an integral over r. So what I'm doing is I'm going back up to this integral right here. And I'm replacing x and y and z according to the parameterization. Right? So I have 2 minus x. X is r cosine theta. That's I. I have a 1j. I have a zk. Z is 9 minus r cosine theta. This is dotted with that cross product that we just did. This is dA. And we iterate the integral. So we have, doesn't matter that we have r and theta. I'll put theta on the outside because that's a little more traditional. That's 0 to 2 pi. 0 to 2. I'm going to dot these, tie these up a bit, little bit, not terribly much actually. 2 minus r cosine theta times r plus 0 plus 9 minus r cosine theta times r d r d theta. And that we evaluate. So again, there are 3 steps that we went through, or 4 steps if you like, 4 different integrals. We had a line integral that we wanted. We did Stokes Theorem, and we got to this version, which we tidied up a bit, so it's up here. Then we parameterized, and we got, if you like, a region integral over r right there. And then we iterated it. And then we evaluate. And so it's the spirit of the problem is the same as the previous one, right? It's just the details are a little more complicated because we have to figure out what sigma is, and that wasn't given. We have to do this business with making sure that we either match or don't match sigma's orientation, but that's just a plus or minus thing. So, but same idea, same thing as the previous question. So let me do just one more. So what we'll do for this one is we'll say, so I'll make it a little nicer. I'll give the C here. I'll say suppose C is the edge of the part of x equals y squared minus 9 with x less or equal to 0 and z between 0 and 5. Let's say with clockwise orientation from the positive x-axis. That sounds awfully verbose, but it'll make sense when I draw a picture. And what we're going to do is we're going to find the integral over c of z squared I plus 5j plus xyk dot dr. So the picture of this. So x equals y squared minus 9. This is a parabola, so it can help to see to just draw a really quick picture in 2 dimensions to help us sort of get a sense. So x squared equals y squared minus 9. This is going to be negative 9 in the x direction, opening forward, or like to the right. And this is with x less than or equal to 0. This is this picture right here. It's a sideways parabola. So when I do this in 3 dimensions, this is what we get, right? We drew a picture a bit like this earlier. So I did that one to sort of prep us for this one. This is our sigma. We have an axis. X, Y, Z. Just for reference, up in this 2-dimensional picture, this is 9 and 3 and negative 3. So here we have negative 3, 3, and up here this is up at 9. It's sort of not drawn to scale. And the Z goes up to here, which is Z equals 5, and down to 0. So in this case, this is the sigma. The sigma, think of it as a bent piece of paper. This is sigma right here. It's the actual piece of paper. C is the edge of this, and it's clockwise from the positive x-axis, which means we're looking at it, and it's going to go clockwise. So the C goes along the top here. Let me thicken that up. It goes along here, goes down the side, it goes around the bottom, it goes up the left, and then joins up again. So that's C. So what happens is, we apply Stokes Theorem. So you can probably see possibly what the orientation for sigma is going to be. So by Stokes Theorem, this original guy, let me circle it because we've been circling it before. This is the integral we're trying to find. So I'm going to apply Stokes Theorem to that. And so I'll call that asterisk for a second. Asterisk becomes the integral over sigma, and again I'm going to take a curl. So when we take the curl, I take the partial with respect to y of xy minus the partial with respect to z of 5, partial with respect to x of xy minus the partial with respect to z of z squared, partial of 5 with respect to x, which is 0, minus partial with respect to y of z squared, which is 0. This is dot n ds. Now in this case, this is where sigma has orientation. So now we need to go back and need to think about the right-hand rule for this sigma. So we saw this earlier, and this is sort of hard to see. You have to curl your fingers around following C, and the orientation that you get, I did this earlier, let me draw a slightly less bendy version of C. If C goes this way, and if sigma is filled in right here, and if we cross our hands around, this is going to go back. If we sort of do our right-hand rule here. So the way we'll phrase this is sigma has orientation in the negative x direction is maybe a good way to see it. Sort of backwards. So Stokes theorem is done. So then we parameterize. Parameterize sigma rather. So the simplest way to do this is we know x in terms of y, and we know that z goes from 0 to 5. So what we can do is we can simply use y and z. So x is y squared minus 9. Y is y. Z is z. And this is with y between negative 3 and 3. So y right there. And z between 0 and 5. And that set of inequalities, that describes the R that we're about to have. Then we do take the cross product, take the derivatives in the cross product. So R sub y is 2yi plus 1j plus no k's. R sub z is no i's plus no j's plus 1k. This is all turning out really nice. The cross product will be 1i. So for the j component, I get negative 2yk, j, and 0k. And then what we do is we look at this and we say, like, well, does this match or not match sigma's orientation? And so the place to look at here is if we look at the x component. This is positive. So this is opposite sigma's orientation. Right, remember, sigma has orientation in the negative up here, x direction. So this is opposite to that. So what that tells us is we're going to have to use minus. So when we do this, we get next step of the integral. So what's happening is this is now becoming this. So this becomes minus the integral over r. Alright, so now whenever I see an x, I have to put in the I component of our parameterization. So I have an xi. So this becomes y squared minus 9i. I have a yj. I have a negative y minus 2z. Those don't change because we're just substituting the same things in. And I have no k's. I'll put in 0k just as a placeholder. And this is dotted with this cross product we just did. dA. And then we iterate. Doesn't matter which order I do these in because everybody's a constant. So I'll do y on the outside. And then I'm going to dot these. because it's not that terrible. We get y squared minus 9 times 1. And then the two minuses when we dot, so I'll just write plus y minus 2z 2y dz dy, and then we evaluate. And again, so just like before, we went through these specific steps. We had this original integral we started with. We did Stokes theorem. We got a surface integral. Took a curl, described a new surface. Then we parameterized and got a region integral, if you like. It's a nice term. And then we iterated it. And so these are the steps you want to try and make a habit of breaking down and doing them individually, because if you trip over them, if you try and jump them, it's so easy if you're skipping steps to make little tiny mistakes. So that is the end of Stokes theorem.